So today what we're going to do is we're going to specifically talk about Taylor and Maclaurin series, okay? All right, so by the end of today's lesson, you should be able to find Taylor and Maclaurin series for functions. If you want to follow along in the book, we're in section 9.10, and everyone should be working on their sequences and series homework packet as well as your accelerated math. So after the end of this lesson, I'm going to go on Renaissance Place, and I'm going to assign all the rest of your objectives for this year. So then that'll be it. Once you get all of those mastered, then you're completely done. And then I will also print out any tests if anyone has any objectives testable. Okay. All right. So we've already seen Taylor and Maclaurin polynomials, but now we're going to convert them into series. However, we're not going to convert them into any old series. We're going to actually convert them into power series. This is actually something that we've already done, but I just thought that I'd add a little bit of drama because some of you like to be dramatic. All right. So what's the difference between what we've already done a couple of lessons ago when we were talking about Taylor polynomials versus Maclaurin polynomials versus Taylor and Maclaurin series? Well, the difference is this right here at the end, the plus ... So without the plus ... if it just goes up to a finite degree, it's a Taylor polynomial, okay? Or if it's centered around 0, it's a Maclaurin polynomial. However, if we continue this forever, so if this is to infinity, so we're doing the summation as n goes from 0 to infinity rather than to some specific n value. So if it's going from 0 to infinity, that makes it a series. So a series just basically means that it's going to go on forever, as opposed to a polynomial. Polynomials are generally speaking finite. So we're going to, if we want to do a Taylor or Maclaurin polynomial, we're going to set it to a certain degree. So we could go to the 3rd degree. We could do a 3rd degree Taylor polynomial. We could do a 5th degree Taylor polynomial, a 10th degree Taylor polynomial, a 100th degree Taylor polynomial, or whatever degree we want. And then so a series is not going to have a degree because it's going to go to infinity. So it's just a Taylor series or a Maclaurin series if you're centered around 0. Okay. So Maclaurin series basically just is when the center is 0. That's basically it. Okay. So just to let you know, generally speaking, when we do Taylor and Maclaurin polynomials, it gives us a good approximation. When we do Taylor and Maclaurin series, it's going to give us an exact value because it's going to infinity, right? So we know that as the degree gets larger, our accuracy becomes greater. And so as our accuracy increases with the degree, if we go to a degree of infinity, it makes sense that our accuracy is going to be infinitely close, or it's going to be exact. All right, so let's go ahead and find the Maclaurin series for cosine. So it's Maclaurin, so that means that we're centered at 0 automatically. And then we're going to go ahead and determine the interval of convergence. And the way that we determine the interval of convergence is the same way that we determine interval of convergence for all of our series. We use the ratio test, right? So we're going to use the ratio, or the limit of the ratio, the common ratio, and that will help us to determine the interval of convergence, and then we just have to test the endpoints to see if the endpoints are inclusive or exclusive. All right, so here, if we do this, we know that in terms of Taylor and Maclaurin, we're going to take the original function at the center, plus its derivative at the center, plus its second derivative at the center over 2 factorial, plus the third derivative at the center over 3 factorial, and then so forth, and then it's going to continue that forever. Now, some of you guys might be wondering, how is this different than just a power series? Like, what's the difference between a Maclaurin and a Taylor series versus a power series? In our power series, our coefficient was just a sub 1. So it was specifically a sub, the first one was actually a naught. The second one was a sub 1. The second one was a sub 2. The third one was a sub 3. The fourth one was a sub 4, and so forth. So in a Taylor or Maclaurin polynomial, we can actually define the coefficient by using the derivative of whatever function they gave us. So if we want to use cosine and I want to figure out what the coefficient of that is, I know for the first term, it's just the original function at the center. Cosine of 0, which everyone should know cosine of 0 is 1. So we know that that coefficient's 1. The derivative of cosine, which is negative sine at 0, which is 0, so the coefficient of the first term is just 0. The second derivative of cosine, which is negative cosine at 0, which is negative 1 over 2 factorial. So now what's happening is with our Taylor and Maclaurin polynomials, our coefficients are going to be defined by the derivative over the factorial of the order of the derivative, right? So if it's a third derivative, it's over 3 factorial. If it's a fourth derivative, it's over 4 factorial, and so forth. And then times our variable of x to the same order, right? So if this is a first degree, then this is x to the first power. If this is a second derivative, then this is going to be to the second power. If this is a third derivative, then this is the third power, and so forth. Okay, so the main difference between our power series and our Maclaurin and Taylor series is that the coefficient now can be determined by the derivative over the factorial, okay, over the order of the factorial, all right? So that being said, of course, we could go ahead and evaluate this, and all the sine of zeros, those are all going to be 0, right? So everyone should know that those are all going to be 0. And so what we get here is if we just simplify that and we remove all of our 0 terms, so basically we're just going to write our non-zero terms, we get cosine is equal to 1 plus x squared over 2 factorial, or 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, excuse me, minus x to the 6 over 6 factorial. And what I like to say is cosine is even. Okay, so if you just remember, all the powers or all the orders of all of our terms for cosine are always even. So that means that right here, this is x to the 0 power, which is 0 is considered even. That's 1. This right here, the next term is x to the second power over 2 factorial, and it's alternating, right? So the first one's positive, the second one's negative, the third one's positive. And so this is going to be x to the 4th power over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and so forth to infinity. Okay, so we could, of course, generalize this. If we generalize this, because it's alternating, we're going to say negative 1 to the nth power. We know our x's are even, so x to the 2nth power all over 2n factorial, and that's plus dot, 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 dot. Okay, so we can now turn this into a summation if we want to, and our summation, and this is going to be our Maclaurin series. This is how we're going to write our Maclaurin series. It's the summation as n goes from 0 to infinity of our nth term, right? So this is our nth term, so of our nth term. So it's a series. If it goes to infinity, it's just a Maclaurin polynomial if it goes to a finite value. So if I wanted to go to, let's say, n equals 10 or something like that, then obviously then that would go to where it goes to x to the 20th power. Okay, all right. So we still have to find the interval of convergence. So how do we find the interval of convergence? And of course, we're going to use the ratio test. So we're going to say the limit as n goes to infinity of the common ratio, of the absolute value of the common ratio. And once again, it's absolute value because we don't care if it's positive or negative, because we're going to add and subtract it from our center in any case. So we just put the absolute value there, okay? So we're just looking for the magnitude at this point, and we're going to add and subtract that to our center. So it's going to be the next term in this series, right? So if this is our nth term, we go to the n plus 1th term, which is this right here, x squared times x to the 2n power. So it's x squared because it's even, so it's going to have to go up by 2, a degree of 2, all over. And if you substitute an n plus 1 into your n, it's going to be 2 times n plus 1 or 2n plus 2 factorial, all over the original. Of course, then what I could do is I could just multiply by the reciprocal. I could cancel. The x to the 2n powers are going to cancel. My 2n factorials will cancel. And what I'm doing here is with this denominator, I'm just saying 2n plus 2. The next term down is 2n plus 1. The next term down is 2n factorial, right? So it just keeps counting down by 1. And so our 2n factorials will cancel. And then we're left with this. And of course, x squared is a constant. Remember, x squared is the value that you're trying to evaluate, right? So that's the x value that you're trying to evaluate that's close to 0. So if I want to evaluate cosine of 0.001, What is cosine of 0.001? I want to evaluate that exactly, right? This will actually evaluate it exactly. That 0.001 is a constant, and so I could factor that 0.001 out. And so here it's going to be 0.001 squared times the limit of this. Okay, so it's going to be times the limit of this. And so the limit of this, of course, this is going to be bottom heavy, so it's 0. So what does that mean if our common ratio gives us 0? And so our rule was, we know that this is convergent as long as our common ratio is less than 1. So that's our rule, right? So as long as our common ratio is less than 1, according to our ratio test, then this is always going to be convergent. And so when is 0 less than 1? Well, it's always less than 1. So because it's always less than 1, then that means that our interval of convergence is negative infinity to infinity. Now, what does that mean, that our interval of convergence is negative infinity to infinity? That means I could plug in any value that I want, any x value that I want, and this polynomial will evaluate it exactly. So I don't even have to be close to 0. I could be at, x equals 11, and it's still going to evaluate it, and it's going to evaluate it very well. And it's not going to evaluate it well, it's going to evaluate it exactly, because it tells me I could plug in any x value that I want into this polynomial, into this series. Actually, it's not polynomial, into this Maclaurin series, and it's going to give me the exact answer. And so now I have cosine as a polynomial. And so think about that. Even if it's an infinite polynomial, I do have cosine as an infinite polynomial or as a series. And so we know that series are so much easier to deal with, especially if we're doing derivatives or integrals or anything like that. And so rather than working with cosine, because we may or may not be able to evaluate cosine of 0.2, right? But we could certainly plug it into our summation and then evaluate that summation. Okay, all right. So that being said, we still have to test, oh no, let's try something else. Let's try cosine of x squared. I don't have to test the endpoints because the endpoints are infinity and negative infinity, right? So the endpoints are never inclusive if you're going to negative and positive infinity. All right, so that being said, we're gonna find the Maclaurin series for cosine of x squared. So how do we do that? And so if you think about it, we just found the Maclaurin series for cosine of x. So how do we find the Maclaurin series for cosine of x squared? And so x is my variable. And so if you think about any time I'm doing anything like if I have sine of x and I do like a u substitution or something like that, I know I could just replace my variable with my new variable, right? So I just have to make sure that if I do a derivative or an integral, that I follow my chain rule rules, right? Okay, so in any case, if I want to find the Maclaurin series for cosine of x squared, all I have to do is substitute in x squared to all of my x's. So it's just basically a composition. I just have to follow a composition. So since we already know that cosine of x is even, right? It's all of our even terms, and it's alternating. It's still going to be alternating if I plug in x squared. So all I'm going to do now is substitute in a x squared into my x term, right? So I'm going to replace this x term with x squared. And so this is going to become x squared to the 2n power or x to the 4n power. And so that's it. This is the series for my Maclaurin series for cosine of x squared. And it's just that simple. It's just that simple. Okay? Of course, we could expand it. If we expand it, it's no longer just even. It's actually x is to every 4th power, right? Every multiple of 4. So it's going to be 0. It's going to be x to the 4th. It's going to be x to the 8th, x to the 12th, and so forth. Because now instead of doubling, it's going to the 4n power, right? So rather than being to the 2n power, it's just to the 4n power. What about our interval of convergence? Well, we could do the same thing. We could basically use our ratio test, and then our ratio test says that as long as the common ratio of the ratio between our next term and our previous term, as long as that's less than 1, we know it's convergent, okay? So if you do the same, basically the same thing, and we cancel and we reduce, we're going to get 0 again because it's bottom heavy, right? The limit of this is bottom heavy. And it makes sense that if our interval of convergence of cosine of x is infinity, is all x, it should make sense that cosine of x squared is also all x, right? So it's pretty much going to be the same thing. Now, is that always going to be the case that if you substitute in an x squared into your x, that's going to give us the same interval of convergence? No, that's not always the case. So in this case, we still want to try to find the limit of our common ratio and then ensure that we know when it's less than 1, right? So as long as it's less than 1, then we know that our interval of convergence will be within that range, within that interval. All right. So let's do the same thing for e to the x. And these are all terms, by the way, that you should, I would say that you should try to commit to memory. If you go on in calculus, especially if you're going to do anything in engineering, these might be useful and helpful for you, okay? Just to know these off the top of your head. But if you don't, it's not a big deal. It's real easy to look it all up, right? So you should just know, though, cosine is even. So that might save you a little bit of time on the AP exam. Cosine's even. Which, if you think about it, if cosine is even, what does that mean about sine? And if you think about it, that means that sine is odd, right? So sine is odd. In fact, one of my students at one time, I used to have it posted on my wall, made me an odd sign of how odd that sine is odd. So they made me a really odd sign about how odd sine is odd. But in any case, so let's go ahead and look at the Maclaurin series for e to the x. So if we do that, once again, we're going to do f of 0. We're going to do e to the 0 power, which is 1. The derivative of e to the 0 power is the derivative of e to the x is e to the x, but we still want to evaluate it at 0, which is still 1. And so we're going to do that. And so what we know is every single coefficient here for our derivative is going to be 1. And it's still over the order of the derivative factorial, right? So this is over 1 factorial. This is still over 0 factorial. It actually works for every single term. So 0 factorial is 1, by the way. This is over 1 factorial, which is 1. This is over 2 factorial, which happens to be 2. This is over 3 factorial, 4 factorial, and so forth. And so if we were to continue this out, it basically just gives us 1 plus x plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial for infinity. And so just by doing this to infinity, that makes it a series, right? So that makes it a Maclaurin series. Let's go ahead and find the nth term. If we find the nth term, it's just basically x to the nth power all over n factorial. And so we could easily turn that into a summation. And so we're going to say it's the summation as n goes from 0 to infinity of x to the nth power all over n factorial. Okay, so now let's go ahead and find the interval of convergence. To find the interval of convergence, we're going to just use the ratio test again. So when is the common ratio, the a sub nth term, a sub n plus 1 term over a sub n? When is the limit as n goes to infinity of the absolute value of that going to be less than 1? So we have to evaluate this. I'm going to multiply by the reciprocal and simplify it a little bit. I could cancel my x to the nth powers. I could cancel my n factorials. And so I'm going to factor out my x because that's a constant. And I'm going to evaluate the limit as n goes to infinity of 1 over n plus 1. And you should know this right here is bottom heavy. So the limit as n goes to infinity of 1 over n plus 1, 0. And so what's that mean? That means our interval of convergence, once again, is going to be all x, right? From negative infinity to infinity. So our interval of convergence is negative infinity to infinity, which means that I could plug in, I could evaluate any x that I want to for e to the x power, and I could do that exactly just using this series right here. So just by using this series, I could evaluate any x value that I want for e to the x, okay? All right, so that being said, let's go ahead and find the Maclaurin series for the derivative of e to the x, which is really easy if you think about it. So we already know that e to the x is this. So then what is the derivative of this? So think about that. What's the derivative of this? So the derivative of this, and remember, this is basically an infinite polynomial, and it's super easy for us to find derivatives of polynomials. That's the easiest thing that there is. And so let's go ahead and see what is the derivative of this, and let's figure out what that does to our nth term. Well, the derivative of 1 is 0, so that just becomes 0. Derivative of x is 1, plus the derivative of x squared over 2 factorial. Well, that's going to be 2x over 2, or just x. The derivative of x cubed over 3 factorial, well, that's 3x squared over 3 times 2 factorial. So the 3's will cancel. So this just becomes 2x over 2 factorial. The derivative of x to the 4th, well, that's 4x cubed. And then in the denominator, it's 4 times 3 factorial, and the 4's will cancel, leaving us with x cubed over 3 factorial. If you think about it, it gives us the exact same series. It gives us the exact same thing. And so the derivative of e to the x is e to the x, which we already know that. We already know that the derivative of e to the x is e to the x, and so it should give us the exact same polynomial, right? It should give us the exact same series, and it does. And it gives us the exact same thing. Okay, and so that should make sense. And so if we want to find the derivative of e to the x, it just gives us e to the x. And we could see that that's going to be true if we just go ahead and find the derivative of our infinite polynomial or our series. What about the antiderivative of f of x dx? What about the integral of f of x dx? What do you think that's going to give us? And everyone should know, well, the antiderivative of e to x is e to x plus c, so plus some constant. And so for us here, we're going to go ahead and antidifferentiate this as well. If you do that, the antiderivative of 1 is just going to be x, right? The antiderivative of x is going to be x squared over 2. The antiderivative of x squared is going to be x to the 3rd power over 3 times 2 factorial, or x cubed over 3 factorial. The antiderivative of x to the 3rd power over 3 factorial is x to the 4th power over 4 times 3 factorial, or 4 factorial. And so it gives us all of our terms. So it's going to give us x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so forth, plus c. So if it's plus c, I'm just going to add and subtract 1 from c. If I add 1 and subtract 1 from c, basically what I could do is I could say 1 plus c, right? So I could just say 1 plus c. So that 1, I'm just taking from c, which c is a constant. And so it gives us the exact same function plus some constant, plus c. Okay? And so it's just going to give us the same summation, the same series, plus some constant, so plus some constant c, which makes sense because we know that the antiderivative of e to the x is e to the x plus c. Okay. Excuse me. Excuse me. All right. So what about x cubed times cosine of x? What's the expanded form of Maclaurin series for this? By the way, this right here is called the expanded form. So if we do 1 plus x squared over 2 factorial plus x cubed over 3 factorial, that's the expanded form of this series, or this summation. Okay, so we want to find that for x cubed times cosine of x. Well, that's super easy because we already know what cosine of x is. We know cosine's odd. And so, I'm sorry, cosine's even. Sorry, sine is odd. So cosine's even. And so we already know that this is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so forth. And so that's already a polynomial, and it's an infinite polynomial. And so what happens if I multiply it times x cubed? Well, I just have to multiply each term times x cubed. That's it. And so in this case, we're just going to multiply this right here, which I do say you should just memorize it. It just makes things easier if you just know it's even, times x cubed. So if I just take x cubed times this cosine function, it's this x cubed times this infinite series. And so if I do that, it's just going to give me x cubed minus x to the 5th over 2 factorial plus x to the 7th over 4 factorial minus x to the 9th over 6 factorial plus da 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 da, and so forth. Okay? And that's it. That's as difficult as that gets. Let's find the expanded Taylor series. So now let's not be centered around 0. So just to let you know, I've been centering around 0, and we've been doing Maclaurin just for the sake of simplicity. But of course, it can be more complex where we're not centered around 0. So for example, if we were doing ln of x, you cannot center around 0 because we know that ln of 0 is negative infinity. And so that's not a real point. And so we always have to use a real point for our center. Okay, so we always want to use a real point for our center. So, so we might have some Taylor polynomial that we have to work with. Now, of course, cosine is not something that we have to be at pi over 4. We can definitely be centered at 0, and it would be easier for us to be centered at 0. But because we've been already dealing with cosine, I want to use something where we've already dealt with it. So we've already dealt with cosine. So how does it change our series if we have a different center? So we're going to be centered around pi over 4. And if you guys remember, what that means is now that means we have to plug in pi over 4 into each of our derivatives. And so that is going to change our coefficient. Okay, so it will change our coefficient. And not only will it change your coefficient, but it's also going to change your x term. So now instead of it just being x to the first power, it's x minus pi over 4 to the first power. Instead of this being x squared, it's x minus pi over 4 to the second power, and so forth. So the x minus, the center, is part of our polynomial. And then we have to evaluate all of our derivatives at pi over 4. So we have to evaluate our original function, cosine of pi over 4, which everyone should know is radical 2 over 2, plus its derivative cosine is negative sine. So negative sine of pi over 4, right? So think about that. Negative sine of pi over 4 is negative radical 2 over 2. And so in this case, what's going to happen is our sine functions are no longer going to be 0. Okay, so it's not going to follow our even, cosine is even. Cosine is even only for Maclaurin series, okay? So it's only even for Maclaurin. It's not even, and there's no rule for it, if it's centered about anything other than 0. Actually, that's not completely true because we could be still centered around pi, we could be centered around 2 pi, and then it's still going to be even. But if it's not one of the axis points, then it's no longer going to be even, right? And if it's centered around pi, you should know that the alternating series is going to reverse, where it's going to start with a negative. So it'll be -1 plus x squared over 2 factorial minus x to the 4th over 4 factorial. So just depending on what it's centered about, you do have to adjust for the center. Okay, so in any case, we do have to evaluate cosine of pi over 4, which is radical 2 over 2, negative sine of pi over 4, which is negative radical 2 over 2, cosine, negative cosine of this, which is another negative, so it's going to be negative radical 2 over 2 over 4 over 2 factorial times x minus pi over 4 squared, and so forth, right? So we have to figure out each of these, we have to evaluate each of our derivatives, and then we have to figure out what this is going to give us. And so we get, once again, radical 2 over 2 minus radical 2 over 2 times x minus pi over 4 minus radical 2 over 4 times x minus pi over 4 squared plus radical 2 over 12 times x minus pi over 4 cubed plus da 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 da. And so that's very difficult for us to come up with a summation that's going to evaluate this, or that's going to represent this, which is why we have to write this, why we want to write this in expanded form. The reason why this is super difficult for us to evaluate is because it goes positive, negative, negative, positive. It's not alternating, right? So this is not alternating. And so it's going to go positive, negative, negative, positive, positive. And so it gives us this awkward pattern. And so we have to be careful for that, okay? All right, and so we're not going to write that as a summation. We're just going to leave it just like that. All right, so let's go ahead and find the Maclaurin series for 1 over 1 minus x, and that we're going to determine the interval of convergence. So once again, since this is Maclaurin, that means that our center is 0, okay? So our center is going to be 0. If we do that, we know that we're going to substitute in 0 into the original function. We have to find the derivative of this, and then substitute in 0. We have to find the second derivative of this, substitute in 0. We have to find the third derivative of this, substitute in 0, and so forth, okay? So if you think about that, that's a lot of work, because this rational expression, we're going to have to keep finding its derivative, okay? If you do that, we're going to get, for the original term, 1 over 1 minus 0, or just 1, plus 1 over 1 minus 0 squared, which is still 1, times x, plus 2 over 1 minus 0 cubed times 2 factorial times x squared, plus 6 over 1 minus 0 cubed times 3 factorial times x cubed, plus 2 over 1 minus 0 cubed times 4 factorial times x to the 4th, plus da 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 da. Okay, so if you just keep finding its derivative at 0, you could evaluate that. And what's going to happen is if you simplify it, I think that I might have a typo here. This is not 2. This should be 24, actually. Sorry. So this should be 24. So that was, I don't know why I have a 2 there. It's going to give us 1 plus x squared plus x cubed plus x to the 4th plus da 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 da. Okay? And so, of course, the nth term in this case is just x to the nth, which is super easy. And so I could write this as a summation. It's the summation as n goes to infinity of x to the nth. Okay, so let's find the interval of convergence. So the interval of convergence is the next term. The next term is x to the n plus 1, or x times x to the nth, all over x to the nth. You can go ahead and cancel that immediately. We could simplify that immediately. And we get the limit as n goes to infinity of x. Remember, x is a constant, so I could just factor it out. So it's actually the limit as n goes to infinity of 1, which is just 1. And so 1 times x is just x. And so we just want to figure out when is the absolute value of x less than 1? When is our limit of our ratio less than 1? And it's going to be less than 1 when x is between -1 and 1. I still want to test my endpoints. So I'm going to plug my -1 into my original series, or my original summation for my Maclaurin series. And I'm going to plug in 1 into this. Obviously, if you plug in -1, it's -1, plus 1, -1, plus 1, or it's going to be, actually, we're going to start at 0. So it's 1, -1, plus 1, -1, plus 1, -1, which is divergent. Okay, so that and -1 is excluded. If we plug in 1, it's just 1 plus 1 plus 1 plus 1 to infinity, which of course is infinity. So that's divergent as well. So that means the endpoints are excluded, and our interval of convergence is -1 to 1, exclusive of the endpoints. Okay? All right, so what happens if I want to do 1 over 1 minus x squared? So now I'm going to change my function to something that's a little bit more complex, which it's really not that complex, because we already saw how we do this with cosine. So if I replace my x with an x squared, my function with an x squared, I just have to plug in an x squared into my Maclaurin series that I already know. So I already know that 1 over 1 minus x is the summation as n goes from 0 to infinity of x to the n. So I'm just going to replace this x with an x squared. I'm just going to substitute in an x squared there. And we're just going to get that it's equal to the summation as n goes from 0 to infinity of x to the 2n power. And that's it. So that's our series. Well, what about our interval of convergence? Well, our interval of convergence, we could also, rather than using the ratio test, we can go ahead and set it up using our summation of a sub n times r to the nth. I could also use this if I wanted to, okay? So if I want to, I could also use this formula. Either way works. Okay, either way works. And you could probably guess as to what our interval of convergence is probably going to be, but let's not guess. Let's go ahead and actually figure it out. Okay. So the interval of convergence, if I were to use, rather than using this, let's just go ahead and use the ratio. I like the ratio test. I think it's easier. It's really not that complex. But if I wanted to, I could set this up like this as well. Okay, where because a sub 1 is 1, I know that my common ratio here, r, is just x squared. So x squared just needs to be less than 1. But rather than doing that, let's just go ahead and do the limit as n goes to infinity of this. We could cancel this immediately. Once again, we get a constant. We can factor that constant out. So once again, our radius, which is x squared, has to be less than 1, which I just said here, right? So we know that this is 1, a sub 1 over 1 minus r. So this is our r. R, which is x squared, must be less than 1, which is what we have exactly here. So our ratio test gives us exactly that, because our ratio test comes from this. Okay, so this comes from this, And so because of that, we could go ahead and just derive it ourselves, or we could just use the rule already established. Okay, so of course, x must be between -1 and 1. If we test our endpoints, if we plug our endpoints back into this original function, basically this right here to the 2n power is just 1 plus 1 plus 1 plus 1 plus 1, because anything even is always positive. And so 1 plus 1 plus 1 plus 1 all the way to infinity, of course, is going to be infinity, which is divergent. We could also do the same thing with 1, which is the same exact thing, 1 plus 1 plus 1 plus 1, which is just going to be infinity, which means this is also divergent. And that means that our interval of convergence is -1 to 1, exclusive of the endpoints, which you might have guessed that because it's basically the same function. We're just substituting in x squared into our x. Okay, so that being said, let's get a little bit more complex. Okay, so now we're going to get a little bit more difficult. I am going to tell you that you're going to see these problems on your Accelerated Math, so it's good that you're here, that you can see this. And we want to use the Maclaurin series to find f of x equals 1 over 1 minus x squared to obtain the series. So we're going to use this function, this polynomial, which we just figured out right here, was the summation as n goes from 0 to infinity of x to the 2n power. We already know that for this. Okay, so we already know that. We want to use that to try to figure out the series for 2x over 1 minus x squared squared. Now, I can't just do a substitution. I can't just substitute something into my x, because this is a much, much, much different function, right? It's not the same function at all. So how do I go about doing that? How do I go about figuring that out? Well, if you take a close look at what we have here, this function, and we take a close look at this function, you might be able to figure something out, okay? And I will say that in the past, I usually will have my students break up into groups, and I'll have them discuss it and try to see if they can figure something out. For the sake of time, because we're online and you guys probably don't want to be sitting there just by yourself trying to think about this, I'm going to tell you that the derivative of this function is this function. So the derivative of this function is this function. Now think about that. So the derivative of this is this. So we know what this is. We know what polynomial or infinite polynomial or what series this is represented by, right? It's just going to be x to the nth power, right? Or x to the 2nth power, because it's x squared. So then that means that we want to find the derivative of that. And so that's going to help us to figure out the Maclaurin series for this right here. So because this is equal to this, we just want to find the derivative of this. The derivative of this will equal this function, because this function is the derivative of this function. So because these are equal and these are equal, or I'm sorry, these are equal and this is the derivative of this. If I could find the derivative of this, it should be equal to this derivative. Okay, all right. So let's go ahead and find its derivative. So what is the derivative of x to the 2nth power? So the derivative of x to the 2nth power is going to be 2n, right? 2n times x to the 2n minus 1. So here we go. So we get 2n times x to the 2n minus 1 power. Okay, so this, which is the derivative of our original function, is equal to the derivative of our series, which is this. So these are all equal to each other. Okay? No, there is one thing that I did do. When I found the derivative of this, I went from n equals 0 to n equals 1. If you think about that, why in the world did I go from n equals 0 to n equals 1? And it's because what happens to the first term, so let me go back a little bit. So sorry, I'm going to go back here. What happens to, and I'm going to actually even go beyond this page, sorry. This expanded form, so here's our expanded form. If you think about it, what's going to happen to our first term, the derivative of 1? And the derivative of 1 becomes 0. So that first term becomes 0, right? So that first term becomes 0. So that first term is going to become 0. It's still 1 for 1 over 1 minus x squared, because remember, I'm just substituting in x squared into my x's. Because 1 has no x's, it's still, the first term is still 1, okay? So that being said, we're not going to start at 0. We're going to start at 1 when I get my next series here. All right? Okay. So let's try that again. So let's say I have here 1 over 1 plus x squared. Okay, so 1 over 1 plus x squared, which is a different function. Okay, so this is a different function. So if I had asked you to do this one, find the Maclaurin series for negative 2x over 1 plus x squared squared. The first thing I would do is I would actually figure out what is the series for 1 over 1 plus x. So I know that there's a lot of steps here. And then once I do that, I could figure out 1 over 1 plus x squared just by substituting an x squared in. Once I do that, I can find its derivative. So the derivative of this gives me this. Then I can find the derivative of my series for 1 over 1 plus x squared. And then I could find my Maclaurin series for this derivative. So there's a lot of things going on here, okay? So that's going to be, the derivative of this is going to be this. So I want to find the series for 1 over 1 plus x squared. So that right there, if I use my common ratio, test, it's going to be here. And remember, a over 1 minus r is equal to a sub 1 times r to the nth power. So actually, if you know that this is the form of a over 1 minus r, if you know that, you could turn it into a summation right away, okay? We could also just find 1 over 1 plus x, and then we will be able to get that as well, and we'll see that it actually is alternating. And then what we could do then is substitute in our x squared, and then we could get this. Or we could just know that if this has the form of a sub 1 over 1 minus r, we could turn it into a summation right away. Now, most functions that we deal with won't have that form. But if it has that form, this is the one case where we could use this shortcut. Okay? All right. So in any case, it's going to be alternating. And it's negative 1 to the nth power times x squared to the nth power, or negative 1 to the nth times x to the 2n power. All right. And so if you think about it, how is this function different than the last function that we dealt with? And the last function we dealt with was 1 over 1 minus x squared. This is going to be 1 over 1 plus x squared. And so this becomes 1 over 1 minus minus x squared. And so because we have that minus in there, this is going to become alternating. Okay, so this does alternate. All right, so now that being said, since I have the series for 1 over 1 plus x squared, it's very easy for me to go from here to the series for this, because I know that this is the derivative of this. And so because this is the derivative of this original, that means the derivative of this series is equal to this. Okay, so then we could say this is equal to the derivative of 1 over x squared, which is equal to the derivative of this series. And so if I find the derivative of this series, it's going to be negative 1 to the nth, that's just a constant, so it stays that, times 2n times x to the 2n minus 1 power. And so that's it. That becomes my series, my Maclaurin series for this fairly complex function, rational function. All right, so let's get even more complex, okay? So I'm going to get even more complicated here, excuse me, where my coefficient, my a sub 1 is -1. It's over 1 plus x to the 4th power, right? So it's plus 1 plus x to the 4th power. Now, this is in the form of my geometric series, so I can use my shortcut for this, just to let you know, okay? So I can use a shortcut because it's a constant over 1, and that 1 is really important, and then plus our x, right? Or plus or minus our x. And so this right here is the derivative of this, just to let you know. So if you find the derivative of this original function right here, it does give us exactly this, okay? So it gives us that exactly. All right, so that being said, let's go ahead and find the series for -1 over 1 plus x to the 4th. And so what I could do is I could write this as -1 over 1 minus negative x to the 4th. And so anytime you have a plus here, instead of 1 minus r, then we're going to turn into 1 minus a negative. It's always alternating. Just know that that's always going to be alternating. So then this becomes the summation, and goes from 0 to infinity of -1, that's this a sub 1, times r. Our r is negative x to the 4th to the nth power. Okay, so this is going to be -1 to the nth times -1. So it's -1 to the nth times -1, or -1 to the n plus 1 power. And then, of course, times x to the 4n power. So now I know the series for this original function, this original rational function. So this is the power series, or the Maclaurin series, and it is power because power just means that we have some coefficient, and then Maclaurin and Taylor just means we know what those coefficients are, right? So it's not just arbitrary, we know what those coefficients are. And so we could just basically say that this is -1 to the n plus 1 power times x to the 4n. All right, so now I know that this function that I'm trying to evaluate, I'm trying to find the Maclaurin series for this. That's what this question is really asking for, right? That's my end game, that's my goal. So that is equal to the derivative of this other function that we were easily able to determine. So the derivative of that function is going to be the derivative of its series. The derivative of the series, because it's a polynomial, it's just going to be this constant times 4n times x to the 4n minus 1. And that right there is the series for this rational expression. And this rational expression is fairly complex, and it would be very difficult actually for us to calculate the summation for this series without doing it using this process. So this process is really the best way of doing it. Figure out for the simple case, and it does say use this to obtain this, because this right here is actually very difficult for us, okay? All right, so let's try it one more time. Let's try this function here, -1 over 1 minus x cubed. Now this is 1 minus x cubed, so that means it's not going to be alternating because it already follows the rule of a sub 1 over 1 minus r. So this is our r, just to let you know, okay? I'll also let you know that if you find the derivative of this, guess what? It gives us this, okay? So it's the same idea. So let's go ahead and see if we can find the series for this original function. And so the series for that is going to be a1, which is -1, times r, which is x cubed to the nth power. And of course, that's just going to be -1 times x to the 3n power, or just negative x to the 3n power. Because this function is the derivative of our original, we could just find the derivative of our series, and this series is a polynomial, and so we know that the derivative of negative x to the 3n power is -3n x to the 3n minus 1. And that's all there is to it. It's pretty simple for us to get that answer, although if we were just working with just this original one, that might be very difficult for us to do. So if you saw this and I said, find the Maclaurin series for this, and I didn't tell you it was the derivative of this, What I would be thinking is, can I anti-differentiate that? Is this the derivative of something? Is there some way I could get this? Because this is really complex otherwise. Well, that's the end of our lesson. Thanks for watching. I hope this was helpful. Bye for now.